when we want to work out the mechanisms, the steps mechanism, when we are given either a full open question where we have to calculate the rate equation and the rate constant, or sometimes we're given those details and we have to work out the steps. There is always a way to proceed. So in whichever way we get to the rate equation, okay, so the rate would always be equal to K, and then concentration of the reactant to the power of their order. So let's use a specific example. In this case, for example, we had iron 3+, and it was first order, and then iodide second order. So it would be to the power of 2. And then the other things that we must keep in mind is the overall equation. Okay, so we know that the overall equation for this reaction, for this redox, is 2 iron reacting with 2 iodide to form 2 iron, but with a different oxidation number and iodine. This doesn't matter the symbols for now, so we'll keep it like this. So to work out the mechanisms, those are the two things that we need to keep in mind. Okay, the rate equation and the overall equation. This is because the rate equation will always give us the stoichiometry of the reactants in the rate determining step. Okay, there are some exceptions, like if the rate determining step involves an intermediate. Okay, but for now, let's just, that if you have to work at the mechanism from 0, that's unlikely that it would come up with a complex intermediate. The thing to know would be this one, that the reactants in the rate determining step, so this lowest one, will include the same stoichiometry as the rate equation. So we know that in the rate determining step, we would have Fe3+ reacting with 2 moles of iodide. And this would give us something. Then we have, so that's the first step, then we have the second step. Before we construct that, what we need to think about always is that if everything has to sum up to the overall equation. So we can construct like a kind of equation system where we keep in mind what is present in the overall equation and what is missing in the second step. So for example, we can complete already the reactant because we know that, well, in the overall equation, we have 2 moles of iron 3+, but in the rate determining step, because we know it from the rate equation, we only have 1 of this, which means that in the second step, there must be another Fe3+ reacting. Okay, and then we can think about, okay, what else is going to be formed. And here you play around a little bit thinking, okay, maybe in the first step, we will have at least one of the products that it's formed. Okay, and then maybe an intermediate. And then that intermediate is what would react further with the second step to then cancel it out and give whatever else it's formed in the overall equation. So using that, why don't you try just thinking about this, about one product, intermediate will react to give whatever other products we have. This could be an example of what happens. And the important thing to keep in mind is that, well, at the end, we know that intermediate cancel out, and we needed to bring together these 2 steps to give us the overall equation in the correct stoichiometry. However, what we could think about is that, wait, is this a likely thing that could be formed or not? And that's where a bit of general knowledge in chemistry is required. For example, iron has a charge of 1+, it's a bit unlikely because we just haven't seen it, because by studying transition metals, we know iron is always 2+ or 3+. Maybe that's why we could think maybe there is something else formed. Okay, but I think that's definitely a good approach. Okay, that can at least make you write something and not keep like a question blank. Okay, but that could be one thing. Let's try to work it out another way, because we have a transition metal and we have a non-metal. Maybe they can form a compound that is an intermediate. Just the thing to think about is what's likely to form something that it makes sense chemically speaking, and so in terms of charges, in terms of bonding. Can you work out a different one? Could be another intermediate, like Fe bonding with I2. That would overall have a charge, actually. So if it's 3 plus and then it would be 1 plus left. Good. And that would be the intermediate that reacts in the second step. And that would form, so because those two would react together, actually, it would give us both of the products in the second step. Good. That's another mechanism that it makes sense. Yeah, because we have an intermediate. But those are the things to think about, like what does the rate equation tells you? How can you use the overall equation to work out the other mechanisms? And then a little bit of logic to work out the intermediate and where the reactants take place. Okay, just one little thing that I wanted to mention. Let's just assume that this is the correct mechanism. One thing to think about is how the rate equation would look like if we had this being the rate determining step. Okay, because if in the rate determining step we have an intermediate, you cannot include that in the rate equation, but instead you would replace that with what forms that intermediate. Okay, so for example, if this, let's just make an assumption, this is the rate determining step instead, we could not write the rate equation with the intermediate in it, but instead of the intermediate, we would write the reactant that make it up. Okay, so that's one of the only tricky things if we have different mechanisms that seems that they don't match the rate determining step. It's probably because there is an intermediate to consider. Okay. Take another example where we have those two reactions, and we know that this second one is the slow step and this one is the fast. And we are required to write the overall equation as well as the rate equation. Overall equation, we will need to put those two together, canceling out things that repeat on reactant and product side. We would cancel out this and this. And the overall equation would be O3 plus O to give 2O2. This is our overall equation. One of them will be a catalyst, just will cancel out, and the other one is an intermediate. Which one is which? The way to remember is knowing what a catalyst and what an intermediate is. Catalyst, it's used up and then reformed, because we know that overall is not used in the reaction. And an intermediate is exactly the opposite. It's formed and then it's used up straight away. This means that the NO2, because it's used up, is formed first and then used up, it's going to be our intermediate. The DNO is used up and then it's reformed at the end of the reaction, which means that it would act as a catalyst. Okay. Next thing, rate equation. We know that the rate equation will focus on the slow step or the rate determining step. What would that look like? Give it a go. So the rate equation always includes the rate constant times the reactants, okay, to the power of their order. Okay. So we know that the rate determining step is the slow one, so it's the second one, which means that we will include the reactants of that equation. To the power of the order, there is no stoichiometric coefficient here, so that's it. However, we've identified that NO2 is it's a catalyst, it's an intermediate, which means that we would not include an intermediate in the rate equation. Instead, we would include the reactant that make it up. So instead of NO, we would write O3 and NO. So a catalyst is included in the rate equation. Okay, so the rate equation for this reaction, if we consider the second one being the rate determining step, would be this one. If instead we had the first step as the rate determining one, so let's use some colors here, so rate determining step. But let's assume that this is the rate determining step and not this one. The rate equation would be different. It would always be rate constant, but then times always anyway the reactant of that equation. So it would just be NO times O3. Yeah, and that's okay because it's a catalyst and the catalyst is included. Okay, so does it make sense? This is the rate equation if the rate determining step is the first, while this is the rate equation if the second one is the rate determining step, which includes an intermediate. So we cannot leave an intermediate in the rate equation, but we would substitute it with the reactants that form that intermediate. Okay, so this is a different type of exercise that we could expect in exam questions, normally worth like maybe 3 marks. Where we have to put the overall equation and the rate equation, knowing which one is the slow step. I hope that clarifies it a little bit. Let's try one more. We have an equation. Let me write it down first. NO2 plus CO. That gives NO plus CO2. We have the rate equation. Okay, and then NO2 to the power of 2. We want to work out the mechanism. Your try. Before you complete this, let's clarify a couple of things. This is the overall equation. So if we have a 2-step mechanism, 1 and 2, that equation, or those 2 equations, they have to sum up to this one. Okay, so this is always something to keep in mind. That's why I think it's useful to write this down as like an equation system. Then we can always assume that the first is the rate determining step, and that's the thing to remember: rate and rate determining step, how they're related. Off you go.
Sorry, I think I'm just confusing myself.
No, that's okay. Don't worry at all about that. So let's think about the things that we know for sure. We know that the rate equation tells us the reactant of the rate determining step. So that's going to be 2 NO2. It's going to form something. Then, what else do we know for the reactants? We know that in the overall equation, we have also CO, but it's not in the rate determining step, so it must be in the second step. CO reacting probably with something else to form the product. But then we also notice that the reactants, they include 1 NO only and CO, which means that one of these NO2 will have to be cancelled out. And it's likely to be in the other steps, right? Because otherwise it doesn't make sense that it stays in the rate determining one. So this is what we can work out just from the overall equation and the rate determining step. Then what's missing is, okay, we needed to fix everything else over there. Okay, so where are the products? And is there an intermediate form? So we just needed to form something with a bit of logic. Okay. 2NO plus O2 could be the product of this first rate determining step. Of course, we have to consider that, in the product, we have only 1 NO, which means that one of these will have to cancel out. Yeah. Anything else that will have to cancel out because it's not in the overall equation? Your O2. Very nice. Okay. Now, we always need to keep an eye on the overall equation. Is there anything else that we need to form or cancel out to have the overall equation? The only thing that it's missing is the CO2. Good. So one of the NO would cancel out when we add these two equations together. One of the NO2 would cancel out. The O2 will also cancel out. So we will have the overall equation. So in canceling out, it makes sense because if we put these two equations together as just one, they would be both in the reactant and products, and overall we cancel out. So I hope that makes sense. I didn't mention it before. Okay, but good. So notice if we have a nice process and a schematic way to do these questions, yeah, hopefully we can work it out in an exam, because we know that we always have to think about the overall equation, the rate equation, and then try to do these two mechanisms, and always keeping an eye on the overall equation.